today we will be doing the D block elements, and the D block elements of course are the elements which are lying in this period of the periodic table. There are a lot of D block elements, and one of the things you should remember is you should memorize them all. You should memorize the places, you should memorize the change in the atomic numbers between the each periods, and you should also be knowing individual groups general properties. So let's just get into it. Okay, so starting with some of the trends observed in the D block elements. So the first thing we can observe is that this is the third group over here, and this is the fourth group over here, and here we have the lanthanides and the actinides. The series will continue onwards, and they place whatever the series which are here, and they place it outside the table like here, as you can see here. So however, these both elements are still in D block and they are still in group number 3. Now the difference between these both atomic number is this is around 21. Now this, you know the magic number of 8, 18, 32. Now that's a magic number which goes on in a series like that. So what you need to remember over here is that in the third group, first number will be 18, and next would be 18, and this one will be 32. And in group number 4 to group number 12, we have this one would be 18, and this difference between the atomic number would already be 32. This is due to the series, this series being present in here. Okay, so that's one thing you should remember, and common question they can ask. And the second thing you should remember is the electronic configurations of the various D block elements. So for that, I found out the easy pattern you can remember. Okay, so you should remember two things: 1, 2, 3, 4, 5. The 7th group number and the 11th group number are very unique. Okay, so let's go from this start. In the first D block period, that is, which is the period number 4, which the D block appears. Okay, so the second thing you should be very familiar with in this periodic table is the electronic configurations of various elements. Now, usually it will be going on with the pattern of 4s2 or ns2 and n-1 whole d0 to 10. Okay, but in some cases it will be a little bit different. Some anomalies will be observed, and I just wrote this. This is the 4th period and the first D block period, which is basically this one here. So here you have to remember a pattern. Here you have the manganese, and the one between the manganese, before manganese, is chromium. Now chromium has 4s1, and that's the only thing you should remember, and it has 3d5. Similarly, this is having 4s1 and 3d10. Now it is having 3d5 and 3d10. As you can observe, it is halfly filled in both in this case, and it is completely filled in this case. So one electron will go from the outermost 4s orbital and it will enter the 3d orbital to make it more stable in a sense. Okay, so this element is chromium, and this element over here is copper. Okay, that's one thing you should remember. And next we have the second D block period. The trend over here is that every single element from the third, which is the 5th group element, till the 7th, and from here till 11th are all having anomalies. Okay, they are not following this exact thing. They are having 4s1. Like in this case, it's having 5s1, and in this one, this element over here will be having 4d4. Here it will be 4d2 and 5s2. Here it will be 5s1 and 4d4. Okay. Similarly, just this type of trend will appear here also. However, in this case, there is another anomaly, which is the 10th element, or the one before, like 2 before the last one. This one will have pi as 0. There will be no electrons in the outermost orbital, and it will be having 4d10. This also also will be having 4d10. However, this will be having 5s1, like all of these one here, this one here, this one here also. This one will be having 5s2 itself. And next we have one more thing is this element is very important. This is polonium, and we should be remembering that very well. And yeah, the 12th element also we can observe in the periodic table, and you have to learn everything. Okay. Next we go to the last and the third D block period. The last one will be having an only in the last but two elements. Length and the length one, and here what happens is they will be having 6s1, 6s1, and this will be having 5d9. You may think that it's like, why is this stable? It will actually be more stable if it is 6s2 and 5d8. Or it's not observed like that, it's observed that this is actually more stable. And this will be having 5d10, and it's not. And the final element will be having 6s2 and 5d10. Now this is a little bit anomalies, and the main requirement for this is so that you can find out the ionic IE or ionic potential differences and whatever not. Okay. So next topic we'll be having is the general properties of D block elements. And okay, so let's start with the general properties of D block elements. So the first thing is the metallic and covalent nature. Okay. Now we know that the outermost for example, let's take the example of vanadium, for example. Okay, we know the outermost configuration of that, which is argon, and we have 4s2 and 3d. 3d3. Okay, so this is the outermost configuration of the element vanadium. Okay, so as you can see that we are having one 4s and one 3d3, right? So if you draw that, we get this D block is having 5, 1, 2, 3. Okay? So this will be the configuration. So what exactly does metallic and covalent mean? So metallic means that the element is able to donate the entire electrons, like in this reaction, Na plus Cl minus, okay, which is in aqueous solution. The electron is actually being transferred from Na, and it is going to Cl. So plus charge will come here and minus charge will come here, and this will form a metallic. This is a metallic character which is shown by the sodium ion. Now, as you can imagine, the sodium is showing this metallic character because of the presence of a S shell electron. Okay. So similarly, the D block elements are also all metallic because they have the outermost configuration as for Ns1 to 2, right? So they are able to donate electrons like that, and therefore they show metallic properties. Now the covalent properties are shown by the D block over here. So covalent bonds are basically bonds like in boron there are 3 electrons, and there is, if you take for example fluorine, it's having like a structure like this. So here the electrons will get shared, and for this to happen you require lone pair electrons. Okay, and what do you have over here? Over here we are having all lone pair electrons, and therefore this shows the covalent nature. And as you can imagine, because there is also a metallic nature and a covalent nature, and if you combine both of them, metallic nature already being very strong and covalent nature is reinforcing the metallic nature of the element in a way, and therefore the compounds formed by the D block elements are extremely stable. Okay, that's another thing you should remember. Next we have the conductive properties, which is seen in the D block elements. Now conductive, you just require to know one thing. The 1B group or the coin group as it is called, comprised of copper, silver and gold. All these three are coins and they're the most conductive in the entire D block, and actually in the entire periodic table the order is like this. Order in the entire periodic table, silver has greatest conductivity, followed by copper, followed by gold and followed by aluminum. This is the only thing which you should remember. Actually, the atomic radius would increase from here to here in the periodic table, and it would also increase like this. Okay. However, in the D block, this part is correct, but this part is wrong. See, in the D block, as the atomic number increases, the atomic radius or atomic size, it will be slightly increased. Okay. So technically, the last element is not having the least atomic radius / atomic volume. The last but few. So in the atomic table, you can see that the last is zinc. So zinc is not the smallest element. The smallest element is actually nickel. Okay, and that's one thing which you should remember very well. Now along the group, so what you can see is that in the third group, okay, scandium, yttrium and lanthanum, actinum, the difference between these both and these both are all like this will be greater, this is greater, this is greater, so the order is like this. Okay. However, in the 4th to the 12th group, which starts from titanium, what is this? Zirconium and hafnium. Okay. Zirconium and hafnium are almost similar. Okay. So the difference will be equal to 0. Almost. Okay. This is due to the lanthanide contraction. Okay. So basically what happens in them is that the Z effective would decrease, changes. Okay. So for example, in the periodic table, the scandium, titanium, vanadium, chromium, manganese will all have Z effective quite high. Okay, it will be higher than the screening or shielding effect which you can see. So here the Z effective is greater than screening. Okay. For iron to cobalt, okay, from iron to cobalt the ZF is equal to screening effect almost. Okay, and from here to here we can see that the Z effective is lesser than the screening effect. So if the screening effect is greater, then the atomic size would be greater. Okay, that's the basic idea between them. Here also you can say that the Z effective is like similar for both of the elements, and therefore it has the difference in the atomic size and atomic volume. Another thing you should remember is phi coni. They are having similar ionization enthalpy, and finally the thing you should remember is that the first D block period, okay, and the second is not having that much difference in the ionization enthalpy, which you know this should be greater. Okay, the second and third is having a lot. Okay, so continuing from oxidation number, oxidation number you should remember is the electrons, is the number of electrons donated or the number of electrons which are accepted. Now because they are all the D block elements are in third period, therefore they are all metals and therefore they all have positive charge. However, the magnitude of the positive charge varies. And the basic rule you have to follow is that the D subshell should be having 0 or D should be having 5. Okay, so if they give iron for example, then you know that it is argon. Okay, 4s2 3d6. Okay, so what looking at this, you can say that iron has 2 oxidation number. So the first oxidation number is the number to take these 2 electrons, outermost electrons, which will be +2. Okay, +2 is the first oxidation number, and the second would be to get it into this format. So it will be +3. Between these both, this is more stable due to the presence of halfly filled D subshell. Another thing you should remember is that this is not the last oxidation number. The group number gives the group number provides largest oxidation number. Okay, that's the important thing you should remember. And another thing you can say is, for some exception cases will be present. For example, for nickel +2 and nickel +4. Now for these both, you can say that nickel +2 is more stable because of the presence of D subshell and the 2 electrons taken from the 4s. And nickel +4 isn't exactly having D5 or D0. Nickel 4+ will be having 4s2 and 3d, and nickel is 2 places ahead of iron, so you can say it's +2. 6 + 2 is 8+, so if you remove 4 electrons, this will form 3d6. That's the outermost configuration. And as you can say, it's not stable, right? Because it's not stable, you may assume that this would be more stable. Oh, it's not so. This is actually more stable, and you should just remember this, as this is an exception case. Similarly, platinum, which is present in the same group, is also the same. +2 is less stable than platinum +4. Then another thing you should remember is copper +2 is lesser than copper +3. Now you can ask yourself, why copper? Copper plus is less stable than copper +2. You may ask yourself, how? Why is it that so? Because as you can remember, copper is also argon, 3s1, 4s1, 3d10, right? This is the configuration of copper. So when you take one electron, the 4s electron will give out the electron and will be left with only 3d10. Now with this 3d10, you can say that it's completely filled. Who is it more stable? However, we see that there is this process which you have to do for finding out the oxidation number. M to M aqueous, okay, with the charge. So what happens here is you first convert this into gas, heat of sublimation, then you ionize it, so it will become M plus ionization energy, and then you put it in water to make it aqueous, okay. For that you will get hydration energy, right? So you can see that this delta H will provide SOP, standard oxidation potential. Now this delta H, if you calculate for Cu plus, you find that it is actually quite less, okay. It's quite less because of having high hydration energy. Okay, so if you calculate the same thing for Cu plus 2, you have IE1 and IE2, right? Here it will be +2, here it will be +2. Now the standard oxidation potential will be greater, and that's the only thing you should remember, these few exception cases. And after that, we go to the trends observed for the oxidation number. Some trends which you can see occur between the same period. Across the same period, higher oxidation number is it keeps on increasing until manganese, and it comes back down, right? That's one thing you can see across the period. And similarly, the across the group, across the period and across the group, the oxidation number doesn't change. Similar, right? However, we can say that the substances formed by higher oxidation number is more stable. This probably is because of their increased radius and their ability to hold more electrons, basically. Okay, so continuing, next we have the colored compounds. Actually, before that we have magnetic properties. So magnetic properties. Now magnetic properties, they are divided into two types of magnetic properties. First is paramagnetic and second is diamagnetic. Okay. Now paramagnetic, you can say that paramagnetic substances which are attracted, and diamagnetic is substances which are not attracted. Okay. Fine. Diamagnetic, correct? Paramagnetic, of course, like I told, it's attraction. It is having some charge present in it. Diamagnetic does not have any charge present in it, and most probable reason why it is so because of the presence and absence of lone pair electrons. So if there are lone pair electrons, okay, if there are lone pair electrons, then it's almost always para, and if there are no lone pair electrons, it's dia. Okay, correct? Right. So basically what you do for this one and the next property is quite similar because they both use the table. You have 4s2 and 3dn. Okay, so you can say that every single element except for example scandium plus, Sc plus, it's having only 4s, it's having actually no, scandium doesn't plus 3, scandium plus 3, it's not having any 4s orbital and it's not having any 3d orbital either. You can say that is diamagnetic. And some other examples like Zn plus 2. Zn plus 2, what happens is they get filled, so there is no lone pair. So this is one thing you should remember for diamagnetic. And for paramagnetic we have a formula, and this is Bohr magneton. Okay, Bohr magneton. Bohr magneton is a sort of units, you can say. It tells you how much. It tells you the attractive pull power or something like that. Okay, just assume it as the magnetic power. You can assume it as. Okay, so this formula is n into n plus 2 under root. You will get some value over there, and that value is the use for comparing between different elements. Okay. And another thing you should note is, for example, if you get some 3.87, then most probable value of n is 3. If you get 4.09, it's 4. If it's 4.72 or something, it's 4. 6.93, 6. Simple as that. Okay. And just check it once before you submit it. This is not always correct. Okay. Now moving on. Next we have the colored compounds. Okay. Normally in the S block we also have colors in S block. However, unlike S block, in S block, if you supply heat, what happens is that the electron gets excited and it gets de-excited. When it goes from the excited to de-excited energy levels, it will give out some sort of waves. Okay, these waves was usually considered to provide the color to the burning metals. Now, in case of D block elements, D block it's a little different. D block, you know that there are 5 orbitals. Okay, dxy, dyz, dxz. dy x square minus y square and dz square. Okay. Now we can divide these orbitals into two forms. This and this is called as lower level, okay, lower energy level, okay, and this is given the symbol of T and G, or sorry, T to G, okay. You should remember this and this, and this over here is called high energy level, given by E naught. The symbol of this is E, no, actually no, it's called EG. The symbol is EG, okay, and this both belong to this. So if there is like a division of energy, you can say that there is, if you supply heat, an electron can go from the lower energy level to the higher energy level, and that's basically the concept, okay. So for color compounds also, you can have two things you should know. For color to be present, you need to be having lone pair electrons, okay. Lone pair electrons is a must for color to be present. And another thing you should be knowing is that this energy, okay, this energy over here. So depending on the energy that is absorbed and released, we have the formula that E is equal to NhC by lambda, correct? So depending on the energy difference between these both, the value of C is fixed, H is fixed, and N is usually is 3 in this case, and this lambda over here, right, this would change for different substances. If lambda is very low, okay, then it is violet, and if lambda is very high, it's red end of the spectrum. In the spectrum, this is if it's low, it's violet end, if it's high, it's the red end. And similarly, you should remember this figure, okay. Now we know big car. Now indigo is not present in this circle. V, P, G, Y, O, R, okay. Now you can say that if it will absorb one wavelength, one particular wavelength, then it will give out the other wavelength in this cycle, okay. This cycle will provide which wavelength it will absorb and which it will give out. So if it absorbs R, it will give out green. If it absorbs blue, it will give out orange. If it absorbs violet, it will give out yellow, and vice versa, okay. It will absorb just that one end of the this thing, okay. And next we go on to, okay, they can ask this, and they can ask you to find substances which are colored. So the condition for that, of course, lone pair electrons, LP required. Therefore I told that it's quite similar to the magnetic properties, okay. So next we go on to the redox potential and the reactions with halogens and oxides, okay.
Editor here, I forgot to mention that the half-life filled D block elements and half-life filled F block elements also do not exhibit any color, because the lone pair element electrons which are present cannot be excited like that, okay.
So next we go on to the stability of halides. Okay, so halides of course are the last but one group in the periodic table. They are consisted of F, Cl, Br and I. The heat of reaction is very high. However, when the reaction is started, it will continue on without any problem, okay. So we can say that reactivity is in the order of this, okay. So this is one important thing you should remember. And the second thing you should remember is that the metals have variable oxidation states, right? Therefore, it forms many compounds. And one of the major things you should remember is this, that whenever the metal reacts with fluorine, okay, it forms highest oxidation state is stable, right? So Cr is having plus CrF6 is stable. V is having plus 4, 5. So VF5 is stable. Correct? Right? So this is another thing. As for other elements, for chlorine and the bromine and iodine, it's not like that. Not for chlorine, bromine and iodine. Okay? It doesn't do that. So after this we go on to one exception case, which is for manganese. Mn is having plus 7. However, it does not form MnF7. Okay? It forms MnO3F. Okay? This is the highest oxidation state for manganese and it forms that. And another thing you should remember is the copper. Copper has a few exception cases. Like for example, copper plus iodine will form Cu2by2. Okay? And copper is having forced the copper 2 halides. Okay? Now let me just read it. Vanadium only fluorides are relatively unstable in lower oxidation states. Okay? That's the thing. Fluorines are stable in higher oxidation state. Fluorines in lower oxidation state. Okay? Unstable. Higher oxidation state, it's quite stable. Next we have vanadium form only VX2 and copper can form CuX. Okay? Copper forms only CuX and vanadium forms only VX2. Okay? That's the highest basically, but copper also it's the highest. And next we have all copper 2 halides are known except iodide. Okay? Iodide, like this equation which I gave you right here, right? This is not possible. So next we want to another thing is this formula. Remember, copper always disproportionates. Okay? Cu plus 2 and Cu with no charge. And that's all you should remember for the block for halides. Next we have the oxocations. Okay? Next we go on to oxides of the block elements. So for stability of oxides, one thing you should remember is oxides is more stable than fluorides too. So at higher oxidation state, it forms the block element, oxygen and the oxidation state. Okay? This is basically the formula over that. So Mn is having plus 7, so it will be having Mn2O7. Cr is having plus 6, so it will be having Cr2O6. Okay. So this is one thing you should remember. It can form it and it is also quite stable at this level. And the other thing you should remember is this one small table. Okay. Acidic, neutral, alkaline. Okay. So you can say the oxidation state will provide the state of acidic or neutral or alkaline in the of the compound. So of the metal oxide. Okay. So if you find out the oxidation number, if it is 5, 6, 7, 8, it is acidic. If it is 4, it's neutral. If it's 1, 2, 3, it's alkaline or basic. Okay? You can easily remember this as this being of course metal and this character shown by non-metal. Okay? You can easily just remember it like that, and so you can remember. Another exception case is Cr2O5. Apheric. So this is having a plus 5, however it's not acidic. Everything else normal. The vanadium or V2O5 is amphoteric also. Okay. This also should know. V2O5 is also amphoteric, even though it is +5. Right. That's all we have in the block. The remaining topics are like the formation of interstitial compounds and the formation of alloys and the catalytic properties of the block elements. For those, you should remember the text, and I will probably insert a voice this thing